Okay, this subsection talks about free variables. So we're going to focus on consistent systems that have more than one solution. Now, if you go back here to this theorem that we just proved, if the R is equal to n, that is the number of pivot columns, is equal to the number of columns in the coefficient matrix, not including the last column. The number of pivot columns is equal to the number of columns in the coefficient part of the matrix. In that case, the system has a unique solution, not multiple solutions. If R is less than n, then the system has infinitely many solutions. And in the proof here, when R is less than n, then the number of free variables is n minus R. Why is that? Because each column that's not a pivot column must be a free variable column, except for the last column, as we've mentioned before. So here we have a formal statement of that proof. Suppose A is the augmented matrix of a consistent system of linear equations with n variables. So it is consistent, so it has at least one solution. Suppose also that B is a row equivalent matrix in reduced row echelon form with R rows that are not completely zeros. Okay, so that means that the number of pivot rows, number of pivot columns is equal to R. Then the solution set can be described with n minus R free variables. That's what we saw just now, is that the number of free variables is the number of columns n, which does not include the last column in the augmented matrix. The n columns here, okay, and the ones that are not pivot columns will be free variable columns. So n minus R is the number of free variables. Okay, so here are some examples. If you have n equals 3, R equals 2, n equals 3, R equals 3, n equals 2, R equals 3. Okay, now in this case seems kind of strange because you have R is bigger than n, but remember this is possible if the last column, the constant column, is a pivot column. All right? So in that case the system is inconsistent, so we don't think about free variables. You can't have a free variable for an inconsistent system. So here we have a summary of the different types of possibilities for a solution. The system of linear equations has no solution, or a unique solution, or infinitely many solutions. No solution means inconsistent. If it's consistent, it either has no free variables, or it has free variables. If it has no free variables, it's a unique solution. If it has free variables, infinitely many solutions. So here's a good diagram. Okay, so if the last column, the n plus 1 column, is a pivot column, you have an inconsistent system. If the last column is not a pivot column, you have a consistent system. In this case, you can count the number of free variables. If R less than n, which means there are free variables, because the number of free variables is n minus R, in this case, there are infinitely many solutions. And if there are no free variables, R equals n, you have a unique solution. So you can characterize this as you have free variables here. Here you have no free variables. Here you have no solution at all. Well, just let's say that this one is no solution. This means at least one solution. So let's look at this equation here. Consistent more variables than equations. So in this case, suppose a consistent system of linear equations has m equations in n variables. If n is greater than m, that is, in other words, if the number of variables is greater than the number of equations, then the system must have infinitely many solutions. In other words, it's consistent and has at least one solution. If it has at least one solution, and there are more variables than there are equations, then it must have infinitely many solutions. Okay, so how does this work? Well, think about how the matrix works here. Let's just draw a little matrix here with signs. Right, now here we say there are m equations, and there are n variables. And we also have this last column. So there are n columns here. Now remember, we said that if you have a consistent system, in order to have a unique solution, the number of columns must be equal to the number of pivot columns. There must be a pivot in every column. On the other hand, you can't have more pivots than you have rows because each pivot takes up one row. Okay. You might have less pivots than you have rows. You might have 0 rows at the bottom, but you can't have more pivots than you have rows. So what does this say? This says that R must be less than or equal to M. That's this conclusion. On the other hand, that means since n is greater than m, that means that R must be less than n. Okay, that's the conclusion here. R is less than n. And we already saw above, when R is less than n, you have infinitely many solutions. Okay, so this gives the fact that you probably learned in high school that if you have more unknowns than equations, then you'll have infinitely many solutions. Now, it is possible you'll have no solutions. That's also possible. If you have at least one solution, you have infinitely many solutions. Okay, so let's see what we have here. Here we have 1, 2, 3 equations in 4 unknowns. So we know that if this is a consistent system, there must be an infinite number of solutions. So now, if someone tells you that this is a solution, which you can check by plugging these variables into these 3 equations, if someone tells you there is a solution, then you know automatically that there must be infinitely many solutions. Now, how to find these infinitely many solutions, we'll talk about more later. So, the rules that we have and the procedures that we've developed gives us a broad outline of how you might instruct a computer to solve a system of linear equations. Remember, this is kind of the goal of this whole section, is figure out how to tell a computer to solve linear equations. But first of all, you'd represent the equations as an augmented matrix. Next, you'd convert the matrix to row equivalent matrix in reduced row echelon form. Okay, there's a standard procedure that you can go through that you can program a computer to do. Now, if the last column is a pivot column, then you know the system is inconsistent. If the last column is not a pivot column, then either R is equal to n, which you can read off from the reduced row echelon form, then you'll be a unique solution. And you can read off the solution from the entries in the last column. On the other hand, if R is less than n, there are infinitely many solutions. So you'll have to find some way to describe it using 3 variables. Now here he mentions that there are some complications in making this actually work out practically, and that's, you can say, the devil's in the details. But we do have a broad outline of an algorithm that we could use to solve, in general, a system of linear equations. Okay, let's stop.